Thanks, Dee. Hi everyone. Today I'm going to talk about something that is related to the theme of the workshop, but slightly different from the techniques of the workshop. What I'm going to talk about is a different way to Gibbs sample. Oh, sorry. So there are going to be two main tasks that I will talk about. The first is a task that all of you know and love, which is the task of preparing the Gibbs state associated with a given Hamiltonian. And then the second is the task of decoding a classical error correcting code depending on the Hamiltonian. And what I will attempt to convince you of today is that these tasks are related in the sense that the left-hand side reduces to the right-hand side. So we can call this idea computation via decoding. And this is not the first time that this idea has appeared. So I'm going to give a brief history of how this idea kind of evolved. So in 2005, Regev proposes reducing worst-case lattice problems to the problem of learning with errors, which is a famous hard problem in cryptography. This can also be viewed as an average case decoding problem. In 2022, Chen, Liu, and Jandry showed how to use Regev's reduction for algorithmic purposes. In 2024, Yamakawa and Jandry proposed a way to get efficiently verifiable quantum advantage without structure. And this protocol is essentially just to solve a decoding problem. So the same machinery powers this proposal. In 2024, Jordan et al. Also found a way to apply this kind of machinery to a new setting, which is namely the setting of optimization problems. And this paper is called Decoded Quantum Interferometry. And finally, today I'm going to talk about a further extension of this idea to the setting of quantum optimization problems. So in order to understand Hamiltonian decoded quantum interferometry, we're going to have to first understand decoded quantum interferometry. So here's a problem setting. You start off with a combinatorial optimization problem that is specified by a tall matrix B and a tall vector V. And we can think of these as being over F2, although they extend to other fields as well. So we can regard this as an inconsistent system of linear equations in the sense that if I were to multiply B times X and I gave you the output of that product and I asked you to find X, that would just be doing your regular linear algebra stuff. But in this case, some of the bits of the output B times X may have been flipped. And I'm asking you to find the X that best fits the B and the V. So to repeat, what you have to do to solve this problem is to find X that satisfies as many as possible of the M linear equations as possible. So M here is the height of this matrix B. So we can equivalently cast this as a problem of maximizing an objective function. The objective function is simply the number of satisfied linear equations minus the number of unsatisfied linear equations. And we are going to give this function a name, which is f. So the key idea here is that you can solve this problem by preparing what I'm going to call a function state. So this function state is a state supported on the computational basis. Supported on bit strings, where the amplitude of each bit string is the value that the objective function of max XOR set assigns to that bit string. So how good is that bit string for the optimization problem? And the purpose of preparing this state is such that upon measurement, you will obtain solution X with probability fx squared. And so the optimal X is output with highest probability. There is actually a modified version of this idea, which is that, if I can prepare fx, the state corresponding to f, I can also prepare the state corresponding to f to the L. And the reason for doing this is that if you just have vanilla state f, then maybe one solution is only slightly better than another solution. So the amplitude of the best solution is only slightly higher than its neighbor. However, if you are able to prepare f to the L of x, then this makes the distribution of your resulting measurement more peaked on the optimal solution. And so you're more likely to obtain the optimal x upon measurement. So this entire algorithm is about preparing f to the L. And what this decoded quantum interferometry algorithm does is that it tells you that you can prepare actually the Hadamard transform of f to the L. And the Hadamard trans is a function of the matrix B in the max X or set problem, as well as the vector V. And somehow preparing this Hadamard transform is kind of easier because it's sparse. So then after that, you Hadamard transform back to get f to the L, and then you do your measurement, and you get the optimal bit string. So how do you prepare f to the L? Well, the idea is that it's actually straightforward to prepare a state that is very similar looking to f to the L hat. So f to the L hat is here, and that's your target. And it's actually not too hard to prepare a Dickey state, which is given up here. So this Dickey state is simply a superposition over all bit strings of Hamming weight L with some prefactor that is, with some coefficient that is +1 or -1, depending on v dot e. So once you do this, the obvious next step is to try and prepare the register BTE. So what you can do is you can just matrix multiply with B. And then this is very close to the state that we actually want to get, except that there is an additional and annoying register which contains E, and we want to get rid of this register. So how can we get rid of this register? So if we can set E to 0, then we can just simply take it out of the superposition, and then you are left with the target state. How do we do this? This is actually a decoding problem. So this corresponds to the problem of inferring E from BTE. Now, we can regard BT as the parity check matrix of some code, and then based on that, based on the value of BTE, getting the vector E is just the problem of syndrome decoding. Yeah, so this is an underdetermined system of linear equations. And so if we can solve this syndrome decoding problem, then we can indeed infer the value of E from BTE, set it to 0, and then remove it from the superposition, and this leaves us with the target state. So this is the general flow of the ideas. So what have we learned here? So we started out with a problem that is NP hard. And we found out that this problem actually reduces to decoding in superposition a code that whose parity check matrix is just the transpose of this matrix B in the optimization problem. So this doesn't prove that NP is in BQP, because that would be too good to be true, because decoding is not efficient for all codes. This is only a reduction, which means that the overall algorithm is only efficient if the decoding problem is efficient. And the decoding problem that you need to solve is something that depends on the original optimization problem, which is specified by B. Decoding is only efficient for certain structured codes, and for the B's corresponding to those structured codes, then this reduction gives you an efficient algorithm. And this is indeed what was observed in the decoded quantum interferometry paper, which claims an exponential quantum speedup for this problem called optimal polynomial intersection, which is just reverse engineering the problem of decoding a Reed-Solomon code. And this claimed exponential quantum speedup is under a lot of fire. I think a lot of people are trying to break this speedup classically, so you can also try to do that. So here's a question you might have. DQI reduces classical optimization problems, like max X or set, to classical decoding problems. What about quantum optimization problems? What's a quantum optimization problem? Well, it's a problem on a Hamiltonian. And why do I call it an optimization problem? Well, so most Hamiltonians that we are interested in are local, which means that they are of this form. So they are a superposition over, they are a linear combination of HJs, where each term HJ acts non-trivially on only constantly many qubits. So we can think of each term as being like a clause. And what we want to do is we want to solve the ground state problem. We want to find the ground state of this Hamiltonian. And every term gives you an energy penalty for unsatisfied terms. So this is kind of like the quantum analog of a constraint satisfaction problem. So our setting is going to be kind of like a special case of this, where we consider specifically Hamiltonians that are Pauli Hamiltonians, which means that the HJs are Paulis. And we also insist that the coefficients of each Pauli must take values that are either plus or minus 1. So yeah, as you might have expected from the previous slide, the set of problems that we can solve where we consider Hamiltonians that are of this particular form is a superset of the set of problems solved by DQI itself. And so for every classical optimization problem, in fact, we can write down a quantum optimization problem, and we can write down a Hamiltonian whose ground state energy problem, or whose ground state actually gives you the solution to the classical optimization problem. This Hamiltonian is of this particular form above. And the ground state of this Hamiltonian is also a bit string, because you can see that it's a diagonal Hamiltonian. And this ground state also gives you the solution to the classical optimization problem you started off with. OK, so DQI concerns itself with these problems in the small bubble here. And it showed that these problems reduce to classical decoding. And what we are going to show is that these problems, for when the Hamiltonian consists of Paulis that may not be just these strings, also reduce to classical decoding plus state preparation. So this is the paper that I'm going to talk about. It's called Hamiltonian Decoded Quantum Interferometry. So again, this is the setting. And I said just now that what we want to do is we want to find the ground state or the ground state energy of H. But in fact, we can do something more general than that. We can, in fact, apply any polynomial function of the Hamiltonian to a superposition of its eigenvalues. So the degree of the polynomial, as you might expect, affects the complexity of this algorithm. So why is this non-trivial? Well, in general, we don't know the eigenvectors and eigenvalues of H, and we don't want to diagonalize H because it's an exponential size matrix. And yet we can prepare the state. So can we achieve the same effect via the quantum singular value transform? In fact, yes, but that requires an additional step of amplitude amplification. And the number of times you need to do that is proportional to the operator norm of this polynomial applied to H. And we do not have to do this amplitude amplification. The cost is that we can only do it for particular types of H. So before I go into how the algorithm works, let me explain why the applications of this algorithm. Well, so in general, we can prepare states of this form. And you can choose this polynomial for your desired application. For example, if you choose Px to be a polynomial approximation of x to the minus L, then that corresponds to a problem of ground state preparation. You can also choose Px to be a polynomial approximation of e to the minus beta x over 2. In that case, you can prepare the purification of a Gibbs state. You can choose P to be anything else, like threshold functions. You can basically apply any function you want to the eigenvalues of this Hamiltonian H. And this gives you like spectral filters as well. So I think before I gave this talk, I received the question, how did you come up with this HDQI algorithm? So let me explain why it is a generalization of DQI. Well, it turns out that the state we prepare eventually with HDQI looks very similar to the state that you can prepare with DQI itself. So recall that DQI attacks this problem called max XOR set. What state does it prepare? It prepares this state. Recall that f is the objective function of the max XOR set, and we can apply arbitrary polynomials to this objective function. Now recall also that classical optimization problems correspond to diagonal Hamiltonians. So in fact, you can rewrite this as a polynomial applied to this eigenvalue, lambda x, corresponding to every state x. For HDQI, what we do is we prepare a state that looks very similar. In this case, because we are working with not necessarily diagonal Hamiltonians, so the eigenvectors may not be computational basis eigenvectors. And so nevertheless, we are still able to apply this polynomial of H onto a superposition of the eigenvectors. There should be another register here which contains lambda I star. But you can see that the form of this state looks very similar to the form of this state. It's directly analogous. So I'm now going to explain the HDQI algorithm. So here's the intuition. I'm going to start by explaining the case where we have a commuting Hamiltonian. Now note that commuting Hamiltonian does not mean classical Hamiltonian, because classical Hamiltonians are those that are diagonal, whereas commuting Hamiltonians still may not be diagonal, but they can be diagonalized. So the algorithm is in fact much simpler in this case. And as mentioned just now, HDQI tries to prepare this state where we are applying some polynomial of every eigenvalue to as the coefficient of the corresponding eigenvector. So, well, how could one prepare the state? You know, it would be great if we could prepare a superposition over the eigenvectors, and then we can just act on it with some unitary proportional to P of H. There is a problem with this naive method, which is that we actually don't know the eigenvectors of H, and we don't want to have to diagonalize H in order to find out. So we use a very interesting fact, which is that the maximally entangled state actually gives us something that looks very similar to this superposition over eigenvectors. In fact, the maximally entangled state, which you may know as this state, is maximally entangled in any eigenbasis, including the eigenbasis of the Hamiltonian.
Sorry, can I ask a naive question?
Yeah.
So how do you choose the phase?
I
mean, is that even a well-defined thing? Sum over eigenstates?
As in,
yeah,
are you complaining that there should be something here?
For each eigenvector, you can multiply a phase.
Yeah, that's true.
So anyone would work? Any choice of phase would work? Or you need that phase to be literally one? I mean, I don't know.
I think that there is, like, all the terms in this superposition are like, they don't have a phase relative to each other. Like, the way you would write...
So any choice, for each eigenvector, you can pick an arbitrary phase, as long as you know which phase it is, and you sum them up. That's the initial state you want. Is that right?
The initial state is exactly the maximally entangled state, which, like...
No, this one's okay, the previous one.
But you...
The previous one, you want to do the sum over I lambda I.
Yeah.
Which phase is well defined?
Oh, yeah. So we want the phases to all be like the same. So like we don't want them to be like out of phase relative to each other.
But you never actually prepare this state, right?
Yeah, we don't actually prepare the state.
You only prepare the one on the left.
That's right.
Okay.
Yes.
Okay. So lambda I star. That's actually.
Yeah, that's the actual thing that we prepare. Yeah. Okay. So so what we are going to do is we are going to try and apply P of H tensor I to the maximally entangled state, and that will give us a state of this form. So there is a small problem here, which is that P of H is not necessarily a unitary, but the DQI pipeline actually deals with this. So we can understand HDQI for commuting Hamiltonians as consisting of two main steps. The first step is that we append a special type of state to the maximally entangled state. And I'm going to call this special type of state the pilot state. And what we're going to do is that we are going to act with operations controlled on the pilot state and acting on the maximally entangled state. So the second step is simply to just uncompute the pilot state, because what we eventually want is only this top 2 lines. We do not want the bottom line. We want to set the pilot state back to 0. And eventually what we hope to get is a state of this form, so that we can just remove the bottom register. So the second step is where the decoding happens, and this is very similar to what happens in DQI itself. So I'm now going to talk about what this pilot state means. So the first thing we need to do is we need to decompose P of H as a sum of elementary symmetric polynomials in these variables. So if you recall, the setting was that H is a linear combination of VI, PI, where PI's are Pauli's and VI's are plus or minus 1. So what's an elementary symmetric polynomial? Well, it's simply a superposition over, the elementary symmetric polynomial in terms of m variables is a superposition of products of those variables where every term in the superposition is the product of all possible choices of k variables out of the m. So what we are going to do is we are going to regard this P of H as a linear combination of such elementary symmetric polynomials. So this is the elementary symmetric polynomial, and each of them has a weight wk. So recall that P is actually, each PI is a Pauli, and when I write P subscript bold y, I actually mean that I'm going to look at all the Paulis in the Hamiltonians, and I'm going to pick out the ones in the positions where y has a 1. So this ends up being a decomposition of PH as a linear combination of Paulis. So then, because I said that we want to prepare this state, PH tensor I times the maximally entangled state. So we can write this in terms of the way we had decomposed P of H in the previous slide as simply a linear combination of such objects, which is a linear combination of Paulis acting on one register of the maximally entangled state. So what the purpose of this pilot state is that it's going to tell you what Paulis to apply to the maximally entangled state. Recall that the pilot state is a separate state that we append to the maximally entangled state. Okay, so the target state is up there. And we are first going to prepare a pilot state of this form here. And we are going to append this pilot state to the maximally entangled state. So that's just going to give us this state. And then it's clear that what we then need to do is condition on the y in this pilot register. We need to apply this v of y and p of y to the maximally entangled state. Okay, so then this obtains the following state, which also looks very close to the target state, except that there is an additional register here, the pilot register, which is not present in the target state, and we want to get rid of the pilot register. So we want to uncompute this. So now this becomes like almost the same situation that we faced for DQI itself. So what we are going to do is we need to solve the problem conditioned on Pauli Py applied to the maximally entangled state, infer the value of y in order to set it back to 0 and uncompute it. So yeah, so this is the problem that we are facing right now. And we are going to regard this as a decoding problem. So there's a bit of housekeeping here. We can pretend that Py applied to the maximally entangled state is simply just a state that tells you exactly what is the Pauli that is Py. And the reason for this is that this Py applied to the maximally entangled state is just a tensor product of Bell states, and those are orthogonal. So we can always just do a rotation to get this. Okay, so there is a fact, which is that every n-qubit Pauli has a representation as a 2n-bit string. This representation is called the symplectic representation. And so we're going to label each Py with the 2n-bit string that specifies it. So we're going to call it sympPy. And so the uncomputation problem now becomes, from each sympPy, you want to learn y. Y is promised to be a bit string of weight L. And the key observation here is that Py is a multiplication of Paulis. When we go to the symplectic representation, this just becomes an addition of Paulis, an addition of the symplectic representation of Paulis. And therefore, sympPy can be expressed as a matrix multiplication in the following sense. So I'm going to write down this matrix that corresponds to my Hamiltonian. How does it correspond to the Hamiltonian? Every column of this matrix is the symplectic representation of one of the Paulis in the Hamiltonian. And so this is going to be, there were m terms in the Hamiltonian. So this is a 2n by m matrix. And the problem of inferring y from sympPy is simply the problem of syndrome decoding. Again, if we regard this matrix here as the parity check matrix of some code, we can regard this y as like the vector of errors, and we are promised that the vector of errors has weight at most L, so that's why this is, again, a syndrome decoding problem. Okay, so now this, the final problem that we have to face for HDQI is just of a very similar form to that faced in DQI, which is that we are given BHT, where BH is this matrix here. And the product of this matrix with some error vector, and what we want to find out is this error vector. So in the end, we started out with a QMA hard problem, and this reduces to decoding in superposition a code whose parity check matrix is this BH matrix defined based on this Hamiltonian. Again, this does not imply QMA is in BQP, because the efficiency of this algorithm depends on the structure of the Hamiltonian, because we're decoding this, this code whose parity check matrix is this matrix depending on the Hamiltonian itself. So for commuting Hamiltonians, that's the entire story. Before I talk about non-commuting Hamiltonians, does anybody have questions about commuting Hamiltonians? Oh, yes?
Have you worked it out for mod P, all this?
So I guess you mean if this is mod P?
Yeah, I guess with your inputs.
So the symplectic representation of every Pauli is a 2n bit string. So I guess it's not really necessary to solve a problem over mod P. It suffices to just solve a problem over F2. Yeah.
Which commuting Hamiltonians can you easily decode?
Yeah, so I'm going to talk about that next. Yeah.
So you omitted normalization for easiness of the notation, but you said that at some point you prepare some linear combination of some things, and does it cause any computational overhead, or you just directly get the thing without any subnormalization?
Oh, you just directly get the thing with the subnormalization.
There's no subnormalization.
That's right.
No post-selection.
The reason is because the place where this might pose a problem is when you are preparing this pilot state here. But you can essentially just prepare this pilot state starting from just acting with unitaries. So it's always going to give you the correct normalization. Any other questions? Okay, great. Okay, so for non-commuting Hamiltonians, the problem is, or the algorithm to solve it is significantly more complicated. In particular, now the way you would decompose P of H into a linear combination of Paulis looks much more complicated than in the past because now H consists of terms that cannot be moved past each other because H is a non-commuting Hamiltonian. And so the new pilot state that you would get for non-commuting Hamiltonians just looks significantly more complicated than that for commuting Hamiltonians. And so for non-commuting Hamiltonians, there are actually two rate-limiting steps. The first rate-limiting step is, as usual, the decoding step here. But the second is this step of preparing the pilot state, because it's not even clear that the pilot state for non-commuting Hamiltonians can be prepared efficiently. But we have managed to find out that for some non-commuting Hamiltonians, it can be prepared efficiently. But I think our algorithm here is not the most simple way to do this. Yeah, so again, the caveat here is that now this overall scheme for non-commuting Hamiltonians is only efficient if both of these two steps are efficient: decoding and the preparation of the pilot state. Okay, so I'm now going to talk a bit about this. Oh, yes?
Sorry, for the non-commuting Hamiltonian, does it mean that I have to decode a non-abelian code, or is it still a abelian code?
Oh, it's yeah, that's a really interesting question. It's still an abelian code. The decoding step actually looks identical.
Okay, would you go through why it's abelian later, or?
I can tell you now. So, yeah, so the only difference between the non-commuting and the commuting step is that this pilot state is now a much more complicated superposition here. But once you have worked out what superposition that is, the overall scheme still only consists of this append pilot state, act with operations, and then do the uncomputation. And the only place in which decoding occurs is the uncomputation. Yeah. So the uncomputation step still requires you to solve exactly the same problem. The problem is simply now that, I mean, like, yeah, so you can, for even non-commuting Hamiltonians, you can write down this matrix, which consists of all the symplectic representations of all the Paulis. And then you just solve the same decoding problem. Any other questions? Okay, so can pilot state prep ever be efficient for non-commuting Hamiltonians? And in fact, yes. And as you might expect, it depends on the anti-commutation graph of the Hamiltonian. So the more non-commuting it is, the harder it is to prepare the pilot state. So what is the anti-commutation graph? Well, it's simply the following. You have your Hamiltonian, which consists of Pauli terms. Some of them do not commute with others. And you write down this graph where all the vertices are all the Pauli terms, and you put an edge between terms if they anti-commute. So for example, for this Hamiltonian, z1 plus x1 plus z1, z2, you put an edge between z1 and x1 because they anti-commute, and you put an edge between x1 and z1, z2. But you don't put an edge between z1 and z1, z2. So you can already see that for a more non-commuting Hamiltonian, this anti-commutation graph is going to have more edges. And in fact, what the pilot state depends on is the following. It's going to depend on the maximum connected component of the anti-commutation graph. This is because the pilot state can be written as a matrix product state. A matrix product state is a tensor network in one dimension. And this matrix product state is, for every site, is a qubit of dimension whose dimension depending on the maximum connected component of the anti-commutation graph. And the bond dimension is going to depend on the degree of the polynomial you want to implement. Now, as long as this bond dimension is polynomial, then the complexity, the time required to produce pilot state is going to be polynomial in n times the dimension of each of these blue things. And therefore, pilot state preparation is efficient if the anti-commutation graph has log-size connected components. So now we talk about finding actual Hamiltonians for which this entire pipeline is efficient. Well, we found an example, which is a spin glass consisting of z-type terms, low-weight z-type terms. Each term is deflected to x-type terms with probability p. And this is a non-commuting Hamiltonian. And we found that if p is a sufficiently small constant, then the anti-commutation graph just percolates into log-size components. And because log-size components means that this pilot state can be prepared efficiently, so this overall algorithm is also efficient. We actually also give classical algorithms for Gibbs sampling some stabilizer code Hamiltonians, and this answers Nathan's question about which commuting Hamiltonians our algorithm is efficient for. So we actually identified a property of commuting Hamiltonians, which makes HDQI efficient for them. But then we found out that the same property also allows you to Gibbs sample in a classical way. And the reason why it even makes sense to talk about Gibbs sampling classically is that these stabilizer code Hamiltonians are stabilizer Hamiltonians. So their eigenbasis consists of stabilizer states. And stabilizer states are efficiently classically describable. So to Gibbs sample from such Hamiltonians, all you need to do is output a stabilizer state, or output a classical description of a stabilizer state with the appropriate probability. And this was quite interesting because the Hamiltonians that we can handle in this way correspond to these ones here. And even quantum Gibbs samplers for these Hamiltonians were not really known and were only developed last year. And I think Angela is going to talk a bit more about that. So what's next? I'm going to conclude with a bit more of a perspective. So my vision is that this paradigm of computation via decoding is very interesting, but it's not very useful because it requires a lot of structure. In fact, as you saw for HDQI, the original problem needs to, or the Hamiltonian in the original problem needs to have some sort of efficiently decodable structure in order for the resulting algorithm to be efficient. And what I would like is for DQI or HDQI to be a general purpose algorithm. So is it possible to get advantage in a more average case setting where even if your starting Hamiltonian or your starting optimization problem doesn't necessarily correspond to some family of efficiently decodable codes, you can perhaps use HDQI to get, or DQI to get some sort of advantage. The second problem is obviously more physics motivated, which is that can we extend HDQI to Hamiltonians that occur in nature, which may not have this plus or minus 1 coefficients. And as mentioned, I think our algorithm for non-commuting Hamiltonians is rather complicated, and I would love to find a way to simplify it. So is there any other way of getting a good pilot state? Could we use Lindbladian evolution to do that? Because Lindbladian evolution seems to be seems to require at least a different type of structure than DQI does. So yeah, with that, I'm done, and I would like to open the floor for questions.